Welcome back to the class on a single phase fully controlled rectifiers. In this year we are going to discuss about the single phase fully controlled rectifier with a RL load. The last class we have seen the R load. Suppose if you take T1, T2 is on at a alpha, it will be turns off at angle phi. When the load is consisting a inductance along with a resistance, the T1, T2 will not be off at a angle phi. That we are going to see the circuit of. To explain the circuit, you have to take the input voltage as a VAB as well as a VBA. This is x-axis, this is y-axis. This is VAB voltage, pi, 2 pi, 3 pi, 4 pi. The VBA voltage is opposite to the VAB. That we have shown with a dotted line. This is VBA voltage. Next we are going to see the triggering pulse applied to the T1, T2 as well as the T3, T4. We are applying the triggering voltage to the SCR only when it is a forward bias. 0 to pi, the VAB voltage is positive. Nothing but A is positive with respect to the B. With that polarity T1, T2 is forward bias, we are applying the triggering voltage to the T1, T2 with a delay angle alpha. Again at a 2 pi plus alpha, T1, T2 is forward bias, we are applying pulse to the T1, T2 at a 2 pi plus alpha. The same manner, the pulses applied to the T3, T4 is at a pi plus alpha and 4 pi plus alpha. This is pi plus alpha, this is 4 pi plus alpha. Now we are going to develop the output voltage waveform from alpha. At alpha, the T1, T2 is on. Once the T1, T2 is on, the load is connected to source through the T1, T2. So the load voltage is equal to VAB voltage. So you have to see how the VAB voltage will be changing from alpha to pi up to this point. In case of resistive load, the current is passing from source T1, load T2, B again returned to the negative terminal of the source. In this interval, the inductance in the load is not allowing the sudden increasing and sudden decreasing of the current. So the current will be slowly increases to the maximum value, again slowly decreases to the zero value at angle beta, nothing but at this point. This is nothing but a extension angle. So from pi to beta, the T1, T2 is forced to conduct because of this inductance. At beta, the load current is coming to the zero. Already the T1, T2 is reverse bias. So the T1, T2 will be turns off at angle beta. From beta to pi plus alpha, nothing but a, from this is beta, this is pi plus alpha. No device is conducting circuit, so the load voltage becomes a zero up to this point. At a pi plus alpha, we are applying the triggering voltage to the T3 and T4. Already it is forward bias from pi onwards from this point. So whenever we are applying the triggering voltage to the T3, T4, now the T3, T4 is on. Now the load is connected to the source through the T3 and T4. So the load voltage is equal to VBA. So from this point you have to see how the VBA changes. From this point to this point. Again, because of this inductance, the T3, T4 is conducting up to the angle beta. Okay, up to this point. Again, no device is conducting in this interval. From this 2 pi plus beta to 2 pi plus alpha. The same circuit operation will be, if you see the current waveform, at this point, the current is 0, the current is slowly increased maximum value and come to the 0 at angle beta. Again from beta to pi plus alpha in this interval, the load current becomes a 0 because no device is conducting the circuit. This is IAB, this is IBA current. It will be starting at this point and ended at this point. Again here in this interval no device is conducting, again load current becomes a 0. This is load current waveform. If we draw the source current waveform, the T1, T2 is conducting, the source current is equal to load current, that is positive. We have to take up the same magnitude and same waveform here. So T3, T4 is conducting, nothing but in this interval. Source current becomes a load current, but it is negative. So we have to draw the same waveform in the below the x-axis. This way. Again here T1, T2 is conducting, here negative. Now we have to find out the average output voltage. What is the waveform is there from alpha to phi plus alpha? The same waveform is repeating. This is the waveform is repeating. So baseline becomes a phi. Now I have to find out the area under this curve. To find the area under this curve, we are using the integration. So average output voltage is equal to 1 by pi integral alpha to beta Vm sin omega t d omega t. This integration is giving a area under this curve. If we complete this integration, Vm is a constant take outside. So Vm by pi cos alpha minus cos beta. The value of beta is highly depending upon how much inductance is presented in the load. The name for the beta is the extension angle. This extension angle generally we are measuring with respect to the zero crossing point of the input voltage. Nothing but from this point, the same manner at this point. Now we are going to keep the circuit operation in the table for the serial number, angle, conduction device, output voltage. From alpha to beta, this is wrong. From alpha to beta up to this point, the T1, T2 is conducting. The output voltage is equal to VAB. Again from beta to pi plus alpha, in this interval, no device is conducting a circuit. So the output voltage becomes a 0. Again, from pi plus alpha to 2 pi plus beta, T3, T4 is conducting, the output voltage becomes a VTG. This is the circuit operation for the single phase fully controlled rectifier with RL load, discontinuous load current. What is meant by discontinuous load current means some duration the load current is 0. Nothing but in this interval, see, no current is presented here. No current is presented in this interval. No current is presented in this interval. This is highly depending upon how much inductance is present in the load. Thank you very much for watching this video of single phase fully controlled rectifier with a RL load.